Good afternoon, ladies and gentlemen. The purpose of this title slide is to get your attention. I don't have time to tell you the story behind the picture. However, it was the start of a massive education experience for me, and I hope in the next few weeks some of you will read my paper and dig into the references and read the story of Sleipner A and see why I speak so highly of Norwegian contractors. I've assumed that most of you are consultants and/or academics. During this next 10 minutes, I hope to convince you that there is widespread ignorance about the processes of concreting, how we should place and compact the concrete that arrives on site. Most of all, I want to challenge you to look at the concreting processes from the inside and not the outside, so we can replace ignorance with knowledge and skill. This is the first of several slides aimed at giving a new perspective to service life design. Actually, it's aimed at restoring the old perspective, which was all about what could and couldn't be done by the construction crew to ensure that the outside shell of the finished structure would achieve the durability requirements for which the concrete mix was designed. Question 1 and question 2 are pretty basic. For example, if you can't get inside a cage like this, it's going to be extremely hard to control the pump hose and vibrators to make sure the concrete is forced out through the outer reinforcement and that no cavities are formed. Likewise, if you can't get into position with a good lighting system, you won't be able to observe the concrete filling up the cover zone. Effective continuous monitoring of the concreting process provides by far the most reliable verification of structural durability. This article was only published 6 months ago. It doesn't speak well of our concreting standards in Australia. However, I believe it is only a special case of the concreting problems that are occurring with deep slabs and foundation structures all around the world. The report concluded that a combination of hot weather, equipment breakdown, low slump concrete mixture and poor workmanship resulted in the concrete consolidation deficiencies. The other contributing factors could also be listed as poor planning, poor organisation and poor supervision. Before being too critical of the construction crew, we should examine the conditions of contract for the work. My guess is that the contract documents were part of the problem. Judging from figure 1, the contractor didn't have enough men or vibrators to do the job properly. Even worse, he underestimated the problems of casting the track wall at the same time as the slab. The project specification should have identified these potential problems and should have required the contractor to submit procedures demonstrating how he would solve them, and these procedures should have been approved before concreting operations could start. These Googled pictures indicate that most pours are hit and miss operations, but why did the Canberra job get so badly wrong? The big problem was the track wall, which had to be cast integrally with the slab. The contractor tried to make the concrete stiff enough to stand up in the wall forms without slumping into the adjacent slab area. He wouldn't have needed such a stiff mix if he'd attached a wide skirt to the inner wall form. Making the mix so stiff made it less able to flow around the areas of congested reinforcement. Because this was a suspended slab, all the poorly compacted areas could be seen when the formwork was removed. Furthermore, the few men he had were tied up in fighting with the concrete in the track wall. There was no one left to guide the pump hose, work the vibrators and actually observe the concrete flowing around the reinforcement. In my estimate, with 2 pumps, it would have been reasonable to have planned for, say, a 6-hour pour with, say, 4 vibrators and 1 observer for each pump hose, as well as the pump hose operator. The rate of placement would have been controlled by the vibrator operators and the foreman, not by the pump hose operator. The sketches on the right show the key features of a procedure which would have ensured there was no non-compacted areas in the slab or track beam. However, the method of controlled vibration illustrated here is a major departure from the requirements contained in most concrete specifications. It's also obvious that the procedure that works will be far more expensive than the one that doesn't work. It requires more men, more vibrators and a slowing down of the concrete delivery rate. No tenderer can afford to base his quotation on using such a procedure unless the project specification makes this mandatory. The specification shouldn't say exactly how the concrete should be placed, but it must clearly identify the potential problems which must be addressed by the relevant procedures in the contractor's concreting plan. The contractor must know that he can safely include the real costs including verification in the relevant tender items. It's not just Google media. Go through the world's major concrete journals, including the glossy advertisements, and I think you'll agree that the generally accepted procedure for placing concrete is dump the concrete in as fast as you can, give it an occasional poke with a vibrator, and just hope everything will fall into place. Sometimes it does, but very often it doesn't. A true procedure identifies the potential problems and risks associated with a process. It defines how, when, where, and by whom the process will be carried out, and also how, when, where, and by whom the process will be verified. We need to appreciate the concept of a special process as defined in the older editions of ISO 9001. When we recognise that welding and post-tensioning are special processes, it should be obvious that all the concreting and pre-concreting processes that take place within the formwork reinforcement assembly are also special processes. Neither testing of concrete samples nor coring of the finished structure can verify that all the concrete in the structure conforms to the specified performance requirements. It is only by continuously monitoring the concreting processes that we can reliably verify the performance of the product. In the light of the recent Genoa Bridge failure, it is noteworthy that during the 1990s in the UK, a 4-year moratorium was placed on grouted post-tension bridges until the post-tensioning industry came up with a comprehensive certification scheme for the supply and installation of post-tensioning systems. This scheme includes the pre-qualification of contractors and their procedures. Amongst other things, the pre-qualification process is intended to convince owners that there is negligible risk of cavities being formed in the protective grout casing around the stressed tendons. There is a desperate need for aspects of that certification scheme for the post-tensioning industry to be applied to the processes of placement and compaction for structural concrete members. This is one of the worst failures I've seen. Of course, it didn't look like this when the top form was first removed. It was only as tendons were stressed that the whole dome began to delaminate. But it wasn't really a stressing problem, it was a concreting problem. The lamination simply opened up the cold joints which had been formed during the concreting operation. The concrete had to be pushed through an upper and lower form only 750 millimeters apart. This gap contained a grid of tendon ducts which would have progressively sucked the flow energy out of the concrete. More concrete would have been injected from other access points so that eventually the dome must have been filled, but the joints remained as layers of potential tensile failure. This picture shows one of several major compaction failures in foundation elements for the Great Storebelt Bridge in Denmark. The Storebelt Authority worked hard to ensure that construction of this bridge would set world best practice for quality assurance contracts. Unfortunately, they put most of their efforts into design and control of the concrete mix and did not adequately consider the design and construction problems involved in getting the concrete into the area that mattered most, the cover zone. So where does ISO 16204 and the principles of service life design come to the rescue of the structures we are building now? Storebelt seems to mark the point where the European concrete specialists decided that the contractors, apart from Norwegian contractors, could not be trusted to build structures which could be guaranteed to meet durability requirements. It was decided that the only way to ensure reliable concrete performance was to design mixes which had the inherent performance capacity to compensate for construction variables, provided reasonable standards of workmanship and site supervision were maintained. Performance type specifications and service life design are different names for the same animal. Under a performance type specification, someone determines before construction starts that if the mix design meets pre-selected durability performance criteria and provided the concrete supply meets standard QA requirements, then the finished structure can be guaranteed to achieve the specified design service life, usually 100 years. We imply that we can verify the long-term durability of the finished structure on the basis of the concrete mix design. I find this amazing. Of course, our specifications make standard assumptions about workmanship and supervision, and these are supposed to be achieved by the contractor's QA and management systems. Our specifications don't say much about how we verify that the contractor's QA is actually working. Owners tend to say, well, that's his business and we won't get involved. However, our specifications show an increasing tendency to require sample testing on the finished structure, which indicates that we often have grave doubts that our service life assumptions were realistic. ISO 16204, the Service Life Design Code, draws all its requirements for structural design and construction from ISO 22966, which is the code for execution of concrete structures. But ISO 22966 is not a specification. It can't be inserted directly into contract documents. However, it is designed to be converted into a project specification. And FIB Bulletin 44, Appendix G, explains how ISO 22966 can be transformed into a tender document, which really can prevent the sort of gross non-conformities that we've been looking at. If we can reliably produce structures where the cover concrete is consistently of the required thickness and quality, then we have complied with option 4 of ISO 16204, the avoidance of deterioration method, to ensure the structure will achieve its design service life. This approach puts the responsibility for structural durability back in the hands of the designer specifier and the construction team. However, Appendix G converts the contractual climate from one of fuzzy, unfulfilled assumptions to one of rigorous discipline and fair and well-documented sharing of responsibility between all parties. Some of you may not know that this happened in Melbourne, just 10 minutes drive downriver from here. I want to stress that Appendix G is not only about preventing durability failures, it is about preventing construction failures. If the requirements for prefabrication of the steel box girder segments had been specified according to the principles of Appendix G, I believe this disaster would not have occurred. I hope you will check out these principles as introduced in my paper, and I thank you for your attention.